Hello and welcome. This lesson is going to be on inductive reasoning. So here are the definitions for this lesson. Inductive reasoning is the reasoning that uses examples. So basically we look at a pattern and we try to come up with a rule or a reasoning on what the next value is going to be. So for example, if I see here 1, 3, 5, 7, I can say that the numbers are going up by 2. So then I can conclude that the next number will be 9. So that's inductive reasoning. You're looking at this pattern and you're coming up with a rule that describes the next number or element in the pattern is going to be. Okay, and that rule is called conjecture. Basically, what it is an educated guess based on the information that you look at. So for example, I could say a conjecture of the sum of two positive numbers is always positive. And then I have what is called counterexample. Basically, it is a specific example that proves that a conjecture or statement is false. So let's say I had a statement that said, all geometry students are sophomores. And my counterexample could be, Amanda is a geometry student, but she is a freshman. So this statement disproves the conjecture or the statement that all geometry students are sophomores because I have a student named Amanda and she is a freshman. So this is what we're talking about today, inductive reasoning. So here we're going to look at some examples and we're going to find the pattern and then describe or make a conjecture on this pattern. So for example, here I see that these numbers are getting smaller and smaller. So I could say that I'm dividing each term by 10 to get the next number. I could also say that I'm multiplying by 1/10, which is the same thing as dividing by 10, every time that I go to the next number. So based on this, I know that the next number will be 0.0004. In one of my classes, one of the students says, we can add a 0 after the decimal point to the next number. That could also be the rule that we could use here. Okay, so now what we're going to do is we're going to write a conjecture based on this pattern that we determined. So we can say each element is 1/10 of the previous element. You can call it element, you can call it number, whatever you feel more comfortable. You could also say each element is the previous element divided by 10. That could be another way of stating the conjecture. So each conjecture that a student finds could be different than the next student. All right, very good. So let's go on to the next problem. The next problem, I have fractions. And one thing that might be easier to see is to either change them to decimals or change it to so that they have the same denominator. Because if you notice, 1/8 and like 1/4 is the same thing as 2/8. And then you have 3/8. And if you multiply this by 4, you're going to get a denominator of 8. So you multiply the top as well by 4, you get 4/8. So we see that this list is the same as this one. And this one is a little bit easier to see that you're adding 1/8 every time you go up. Okay, so you are adding 1/8 and then 1/8. So that means the next term will be 5/8. So that's our next term. Just like in the previous problem, we found the next term. Now, once we found it, we want to write the conjecture. Okay, so we could say each element or each fraction is plus 1/8 of the previous element. Or you could say each element is the previous element plus 10, plus 1/8. All right, let's go on to the next one. The next one, we have alternating numbers. Basically, one is negative, one is positive, one is negative, one is positive. When that happens, you pretty much know that this is probably going to be multiplication or division, because every time you multiply or divide by a negative number, you change the sign. So right here, what number you multiply 1 to get 3? Well, it would be 3. So 1 times negative 3 is 3. 3 times negative 3 will be negative 9. Negative 9 times negative 3 would be 27. And to find the next number, then we just multiply by negative 3. So that would be 81. And in this particular problem, they ask for the two next elements. So let's go ahead and multiply by negative 3 again. And by the way, here this is negative. So this would be positive 243. So there we found the next two elements. And as always, let's go ahead and write the statement. So each element is negative 3 times the previous element. And now if you like, you can stop the video and try the next problem and then see what you get. Let's see what's happening to each number. Each number is increasing. And so that means either going to be multiplication or addition. Well, we decide that it's going to be multiplication because we're multiplying by 2 each time. So that means the next term will be 16. So here we write each element is 2 times the previous element. Okay, so that's basically what we're doing up to this point here. We're looking at different patterns and we're making observations, and we're using that observation or that conjecture to make a prediction to the next number. And we're also writing that conjecture in words. Here's another problem here. Complete the conjecture based on the example. So here I have some examples, and here we have the beginning of a conjecture, the product of two odd numbers. So if you notice here, all of these are odd numbers, and when we multiply the result, what do we notice? When we notice that all of them are odd number. So the product of two odd number is an odd number. This one here, we have the beginning of a conjecture, and what is asking us to do is to find some examples and then finish the conjecture. So the sum of an even number and an odd number. So let's say I choose 4 as an even number plus 5, the odd number equals 9. And let's find another one. Let's say I make 10 plus 11 and I get 21. Let's say I get negative 12 plus 5. It's going to be equal to negative 7. So when we make those examples, we notice what? That when we add an even number and an odd number, we get an odd number. So is an odd number. All right. Now, next examples, we're going to use something called counterexample. We're trying to find a counterexample to disprove these conjectures, because basically all these conjectures are false, and we're trying to find a counterexample that's going to show us that this is a false conjecture. So basically, we just need to pick numbers and try to figure out a way to find a counterexample. So let's say I start with 5. If I do 5 squared, is that going to be bigger or greater than 5? Well, 5 squared is 25, is greater than 5, so that is not a counterexample. And let's say I pick 6 squared, that's 36. Is that bigger than... All right, so these numbers are not working. So let's try, like, for example, 0. 0 squared, is that bigger than 0? 0 squared is 0. 0 is not greater than 0. It's equal to 0. So this one would be a counterexample. Another one that could work would be 1. 1 squared is 1, and it's not greater than 1. So that one is another counterexample. Another one that you could do is numbers between 1 and 0. So let's say 1/2. If I do 1/2 squared, would that be greater than 1/2? Well, 1/2 squared is 1/4. So 1/4 is less than 1/2. So right here, I could have used any of these three as an example or a counterexample of this statement. Okay, this ones here do not work because these are greater, but this ones did show me that this guy here is equals to this guy is equal to this, and this one is actually smaller than this one. So all of these three could be a counterexample. All right, supplementary angles are adjacent. Okay, well, first of all, what is adjacent? Okay, adjacent are two angles that are touching each other. So, and what I mean by that is, let me do an example here. Okay, let's say I have these angles right here. And let's say we call this A, and this B, and this C, and this D, and here's the vertex E. So let's say this is the pink one, this one will be the green one, okay, this will be the black one. So when I look at these three, I can say that the red with the green are adjacent, the green with the black are adjacent, but the red and the black are not adjacent. So the reason why these two, the red and the green, are adjacent is because they are touching each other, they're sharing a side. Same thing with the green and the black, they're sharing this side right here. But the red and the black are not sharing a side, so that means they are not adjacent. So to be adjacent, they have to share the side. So the question is two supplementary angles. Well, we know the supplementary angles are angles that add up to 180. Okay, so let's go ahead and put like this. And so right there, I have two supplementary angles and they adjacent. Well, in this case, they are. Well, remember, supplementary angles does not necessarily have to touch. So let's say I have these two angles like here, and let's say this is 120, and let's say this is 60. They are supplementary, but because they're not touching, they're not sharing a side, they are not adjacent. So that means this would be my counterexample. I have met the condition. The condition is they're supplementary, but I have not met the conclusion. They are adjacent. All right, let's go on to the next one. The next one says the sum of two odd numbers is odd. So just pick two odd numbers. So let's say I pick 5 plus 7. Okay, and 5 plus 7 is 12. Right there is my counterexample because I should have gotten an odd number according to the conjecture, and I got a 12, which is an even number. So right there, I'm done. That's my counterexample. The next one is to find an example where 5n is not greater than n. So let's try. So let's say I pick 2, and if I pick 2, 5 times 2 is 10. That's bigger than 2, so that doesn't work. So let's try picking negative numbers. So let's say I pick negative number, negative 2. So 5 times negative 2 is negative 10, and negative 10 is not greater than negative 2, so that would be an example. Okay? Another example will also be like if I multiply by 0. 5 times 0 is not greater than 0, because 5 times 0 is 0, that would be equal to 0. Okay, same thing with 1. So here are two examples where I could use this as a counter example. This one I had to make a little bit smaller so I can fit the whole problem, but basically here we have an SAT and ACT question that deals with these types of problems. And the problem says that Ray made the following conjecture. If 4 points lie in a plane, that the points are collinear. Which figure is a counterexample of the conjecture? Well, so basically here I have the condition. If 4 points lie in a plane. Okay, here I have 4 points in the plane, 4 points in the plane. This one I don't have it. This one I also don't have 4 points in the plane, nor this one. So off the bat, I'm able to eliminate 3. And the question is, then the points are collinear. So if you notice right here, these 4 points are on the plane and they are collinear. So that kind of proves the conjecture. But this one has 4 points on the plane, but they're not collinear. So this will be our counter example. Okay, so there we go. The next one says Maria drew the sequence in figures shown. So here we have these figures, and which of the following is the best conjecture Maria can make based on the figures for n greater than 2? Well, if we look at the multiple choices give us a little bit of more information because all of them starts with n is the non-collinear points. So if you notice right here, I have 2 points. Here I have 3 points. And I have 4 points. So basically, n is the number of points. And if you continue reading the multiple choices, you can draw n minus 1 distinct line segments. So here we're comparing points with line segments. So with that, so here, how many line segments we have? We have 1. Here we have 3. Here we have 1, 2, 3, 4, 5, 6. We have 6 line segments. Okay, so all right. With that being said, let's check it out. Given the n non-collinear points, you can draw n minus 1 distinct segments. Well, let's check it out. If I have 2 points, so I plug it in 2 minus 1, I'll get 1 point. That works. How about if I try 3? 3 minus 1 would be 2. According to this, I should have got 3 lines, segments, and I didn't, so that's false. This one says given n collinear points, so let's say we start with 2, you can draw 2 or n distinct line segments. Well, that's not true because I only was able to draw only 1, so this is false. The next one says if I have n collinear points, you can draw n plus 2. So let's see. We start with 2, and then 2 plus 2, I should have gotten 4 lines. I did not. So that's false. Let's try the next one. Next one, I might have to do a little calculation. So we're going to start with the first example. 2 points. We plug it into the formula, right? We're going to plug it in 2 points here, 2 points there. And let's see. 2 minus 1 is 1. 1 times 2 is 2. Divided by 2 is 1. So that works for this. Let's try the 3. 3. Then we plug it in 3 minus 1 over 2. So 3 minus 1 is 2. 2 times 3 is 6. 6 divided by 2 is 3. And that matches what we got there. Let's try the last one. We have 4 points. So we're going to plug it in. 4 for n. And let's see if it's going to give you us the 6. 4 minus 1 is 3. 3 times 4 is 12. 12 divided by 2 is 6. It did give us the numbers on the pattern, so that means this is our answer. All right, let's continue on to the next problem. Okay, next problem says a student named Terence claims that if 2 angles are supplementary, then they are a linear pair. Okay, well, what is a linear pair? Okay, a linear pair is when 2 angles touch each other, so they're adjacent, and they form 180 degrees. Okay, let's look over here. First condition is that 2 angles are supplementary. Well, these 2 angles are supplementary. These 2 angles are supplementary. These 2 angles are supplementary because remember, supplementary means add up to 180. These 2 are not supplementary, so off the bat, we can eliminate that one. Now, the conclusion is that they are a linear pair, and we're looking for something that disproves that. So here we have a supplementary angles, and they do form a straight line, so they are a linear pair. Here we have 2 supplementary angles, they form a straight line, they are linear pair. And right here we have 2 angles, they add up to 180, so they're supplementary, but they do not touch each other, so they are not a linear pair. So that our counterexample is letter B. And so now this concludes our lesson. I hope this was helpful. And with this, you'll be able to do the practice problems. Thank you very much for your time and have a great day. Bye-bye.